Get away, maybe.
So hi everyone, I'm Liddy, add-on working on Google Chrome. We're here to talk about Z standard on the web, some of the benefits and status on it so far. So starting with some of the quick background about Z standard, it's a data compression scheme designed by Meta, specified in RFC 878. As Meta describes it, it's a fast lossless compression algorithm targeting real-time compression scenarios at zero level and better compression ratios. So in the browser, we're essentially expecting the most benefit from compressing first views and dynamic content with higher compression ratios than gzip and less CPU costs than broadly. The mechanics for signaling Z standard support are pretty straightforward. We add Z standard to the accepted coding header in the request, and the browser decompresses it based on the content encoding header. There are several major deployments supporting Z standard today. Meta uses Z standard for all of its content coding across its apps and resources. They report massive wins for both page load times and CPU savings, and Akamai is also being using it internally for at-rest log storage and observing improved speed compared to gzip with smaller files. And Android also uses Z standard widely. So coming to the performance benefits, Z standard provides more efficient compression, meaning we can either get a similar compression ratio to broadly level 5, which is often used for dynamic content on the web, but compress faster, resulting in less CPU time and lower resource costs. Or we can get better compression ratios for similar times, resulting in fewer bytes spent transferring the content and thus less time used for those transfers. We also get faster decompression across the board based on local benchmarking. So overall, we'll be able to provide faster page loads for end users, and there's lower costs for providers. So coming to the current status in Chrome, we landed support behind a flag in Chrome 117, and we're running an experiment in Chrome 117 as well. It just released a stable this week, so I don't have data I can share yet, but on beta, we've been seeing good results so far. On Windows, we're seeing a 1% improvement in LCP at the 75th percentile. This is a for apples to apples comparison for Z standard supported page loads instead of global LCP. And similarly, there's a 4% at 95th percentile and 5% at 99th percentile. Also keep in mind that the beta channel is not representative of all users, and the results may change in the stable channel. As an aside, we've been talking about compression dictionary transport in the working group, so I just want to mention that shared Z standard support is also available in Chrome 118. If you want to try it, register for the ongoing compression dictionary transport origin trial, and if you enable the feature flag and use the right content encoding header, it should work. The Z standard work complements the shared dictionary work. Plain Z standard will get wins over the plain broadly or other schemes, and compression dictionary transport will give you additional wins over that. So I think there's one issue we'd like to discuss.
Yes, okay, so that's amazing. Part of my slide is not showing. Maybe it's because it's super light, I don't know. It shows, looks very nice on my, oh. It's not displayed, it's some. Maybe you just need to re-enter the slideshow. No, that's,
Yeah.
that's weird, okay. So this would be another explanation if you could see it, but that reference is basically an instruction that the compressor inserts into the compressed stream, saying to copy a certain number of bytes from a previous location in the output.
Exit full screen, then I can see it.
Yeah, can I make a suggestion? You open speaker view instead of hitting slideshow, it won't go full screen, it might work. Yeah, presenter view, fingers crossed.
It's just exit full screen. This will be fine.
Just imagine that it's there.
There you go.
We can believe.
Yeah. Perfect.
Oh, it's animated. It probably will fit with the next
if you like try to advance one slide, it might show up.
No, it's not animated.
Never mind.
It's just not working.
I'm like, gentlemen.
So this slide here depicts a situation where the compressor is going to generate a div tag, and it copies the div tag from a previous location inside the decompressed input. Next slide. So window size, also it's referred to as a sliding window because it stores the last n bytes of decompressed data, where n is the largest back reference that the compressor will emit. So when the decompressor sees a back reference, it has to be able to go and get that data, so the data has to be in memory, and thus the implementation uses a sliding window, which is just the last n bytes. The larger the window size, the better compression you get. gzip supports window sizes up to 32 kilobytes, which means we will store up to 32 kilobytes of the decompressed output in memory in order to be able to satisfy back references. zstd supports window sizes up to 2 gigabytes. We're not going to be storing 2 gigabytes of the output in memory anytime soon. Next slide. So we come to the window size issue, which is kind of a question of defaults. The Z standard command line defaults to 128 megabyte window size. Fortunately, it doesn't always request 128 megabytes. It will request less if the file isn't that big. So if your file is only like 32 kilobytes, then it will request a smaller window size. Sorry about that. Chromium accepts up to an 8 megabyte window size. So what happens is that in the header of the compressed data, there is the window size is included. If we see a window size that's larger than 8 megabytes requested, we immediately error the stream. We don't read anything else. The results isn't loaded. So this means that if you naively create your input using the zstd command line without any options, then as long as the file is less than 8 megabytes, everything will work fine. But as soon as you compress a file larger than 8 megabytes, it will try to use a larger window size. At that point, Chromium will reject it. There's also 8 megabytes was actually, so we initially didn't put an explicit limit in Chromium, which meant we got the default limit that is that the Z standard library uses, which is 120 megabytes. But based on a recommendation in the RFC, the Z standard RFC, somebody from Facebook provided a patch to reduce the maximum window size we would accept to 8 megabytes. So we are essentially compliant with the recommendation of the RFC. The recommendation is for cases where you're accepting data from untrusted inputs, because obviously if someone requested a 2 gigabyte window size, then you would try to allocate 2 gigabytes of memory and crash, which would be bad. So although this slide doesn't cover it in much detail, there's a kind of additional issue that if you just use the Z standard library with the defaults as it comes, you will get 128 megabytes window size, which will then be incompatible with Chromium. So we've got kind of interoperability issue where we need to make sure that all browsers align on using the same maximum window size. Otherwise, will have a bad situation where things work in one browser and not others. We have a developer usability issue, where if a developer just naively compresses with default settings, they will get output which works as long as their input stays less than 8 megabytes. So if they've got a JavaScript file that's 7 megabytes and they turn on zstd with the default settings, everything will appear to work. And then a few months later, when that Java file has grown to 8 megabytes, suddenly Chrome will no longer accept it anymore. What we're here for today is to discuss potential solutions to these two problems. Firstly, how do we make sure that implementers align on accepting the same window size? And secondly, how do we do our best to prevent developers from shooting themselves in the foot?
Is that, should I stop the recording to discuss?
Oh, yeah.
Yeah, okay. So, thank you.
No fancy. Cool. So yeah, so this is going to be sort of a quick update on how Chromium is now supporting animated content in LCP, and hopefully on how we can start extending the specs so that other implementers can do the same. So the status quo, at least according to specs and according to Chrome's implementation up until very recently, is that video content is effectively ignored. Even though, like very often, video-heavy sites, this is the most important content on the page. We would only take into account poster images because they are effectively images. But that doesn't catch a lot of things. That does not catch, specifically doesn't catch autoplaying videos that tend not to have posters because you don't need them. This is mitigated a little bit by the fact that videos with sound, for instance, can't be autoplaying and therefore require a user interaction to start. And the user interaction is necessarily going to cancel the LCP algorithm. So in those cases, this wouldn't have been as big of an issue. But for autoplaying muted videos, if that's the thing on the page, we miss it entirely. Just a complete black hole. At the same time, animated images, animated GIF, animated PNG, those do trigger LCP, but at the wrong time. The way the development timing works, we only issue the potential LCP candidate once the image is completely available. Basically meaning that the whole thing has downloaded and been decoded. And for a lot of larger animated images, this can be long after the animation's actually started. There are some animated images that never complete, right? There's a way of doing video streaming essentially, where you just open up an animated stream and just continue sending frames forever. In this case, that basically can't be LCP. So what we've done in Chrome, and this has been a long time running, I'm sure we talked about this before, I know we talked about it at some of the other working group meetings, is as of Chrome 1.16, and Chromium embedders should get this at the latest in 1.18, both videos and animated images will trigger an LCP candidate the first time that a frame actually renders to the screen. For videos, it won't matter if that's a poster or actual video content. For animated images, that's right, first frame as opposed to first frame after it loads. And this is basically rolled out to Chrome clients at least this week. No. Right. Yeah, we've announced this on like all the channels that we can sort of get to WebPerf, to developer groups in the Chrome changelog, Blink Dev, I think. Just want to make sure that people are aware of this. If you are running a video heavy site, like this is going to impact your LCP in potentially negative ways. We looked globally while we were running this at sort of a 1% experiment level and saw probably a roughly 1% drop in LCP. And obviously, we're still looking now that we've gone to a stable at 100%. We'll follow what happens with that. There are some challenges in getting this into the spec. Animated images are currently mentioned in HTML, as a possibility for the content of an image element. But the animation timeline itself is not actually defined, and there's no sort of callbacks anywhere that say, at this point, an image has actually been presented. Similar with video, the video playback is defined fairly well, but we don't have any sort of timing points for frame display. And we may likely need to extend either element timing, or we talked in this group this week about taking those bits out of element timing, putting them in page timing, and adding some wording into page timing to say, hey, this is the time when a video frame has been displayed to the user. This is the point where you should consider triggering LCP. And when we do that, I think the question naturally arises, should we be exposing these times through the element timing API? Right, as it is, element timing, if you put that on an animated image, is going to give you what we currently report for LCP, which is the presentation time after it's fully loaded. Should we be extending element timing to have a field which is like first frame? So this would apply to things like videos, animated images, possibly progressive images. But maybe this is another timing point. Michael was talking about different timing points yesterday, I think. That's information we should just have about exposed. But that is things we can talk about in the next 18 minutes.
This is just an introduction to some current experimental work at Mozilla that we're doing. And it's trying to come up with performance metrics for measuring how web browsers interact with accessible technologies. So next one. So I'm just going to go through some things really quickly, and I'm hoping the majority of this will be some kind of discussion because I'm really trying to smoke out industry best practice here on how we are performance testing accessibility. That's really the main goal of this discussion. And I'm going to start with our motivating question. I'm going to go through a really quick background on accessibility. I'm not going to go into details on accessibility. I'm going to talk about some of the work that's going on at W3C and other groups. I'm going to just discuss and explain what we did at Mozilla. I'm just going to talk about some of the problems and open issues we ran into. And then I'm going to really try and hope to get some kind of response from the rest of the industry as to how to proceed here. So next slide. Here's our motivating question. And it came to us at FOSDEM earlier this year when we announced that we were working on, when I say we, let me just say it's the performance team and the accessibility teams at Mozilla are working in collaboration to try and solve this issue. But the question we got when we presented our initial work was, hey, I'm a web developer and I'm creating new content and I want to try to make sure not only is it correct for accessible users, but given the choice of different ways to create things, I want to choose a path that's the fast path for accessibility. How can I evaluate new web content for this? What kind of tools does WebPerf give me to do this? And how do I know, how can I avoid things that are known bad? So, and ideally do this in a way to catch it at the design phase and not kind of clean up messes after a site has been fully architected. So that seems like a pretty relevant discussion, and I hope everyone agrees that's in context. That's within scope of this group. And then just really quick background on accessibility, because I know that we're not all accessibility experts here. In general, the number of web users who need accessibility tag is increasing. This is due to the demographics in the world, also due to kind of post-pandemic, pandemic, wherever you are in that. the situation, there's been a marked increase in disability. And then basically, in terms of accessible technologies, what we see at Mozilla in terms of instrumentation and telemetry is that screen magnification is the most used accessible technology. And after that is screen readers and on-screen keyboards. So it's just a general ranking of how we would approach this and size it. And then I'm skipping through a huge amount of tech here. Just general, super quick 10,000-foot elevation view of accessibility. It's like in a web browser, you load a document, create a DOM, you're creating a separate accessibility tree, and then you're using that accessibility tree to deal with an accessible device like a screen reader or et cetera, et cetera. So there is some existing work at the W3C on this issue. There's work on WebDriver, and there's been initial integration into WPT Test Suite as part of Interop 2023. There's been some nice initial momentum here, and it's going to continue in 2024, but the test harness part of this is starting to be solved, but the kind of performance part of this, and that's the parts that are being solved right now are more about conformance and correctness and not about, is this performance, which is our real motivating question here. So what did we do at Mozilla when we were thinking about trying to test this? So first of all, I just wanted to put in a huge caveat here is that this is all in the lab. We are not doing any run testing on this. So just keep that in mind. We would love to be able to do run testing, but I'm going to show a little bit later why this is a little bit hard for us. The first thing we did was run our existing page load test with accessibility on and with accessibility off. These page load tests are just using browser time. It's not nothing special sauce here. These are just what we consider standard industry benchmark. And then the second thing we did was, and the results of running accessibility on off are that, with no screen readers, we're hoping to see browsers not incur a huge overhead for just allowing accessibility with no assistive technology. That is mostly true. And then the second approach that we used was we were running the same page load tests with accessibility enabled and screen readers on. And this was instructive for us because we wanted to see kind of how existing WebPerf dealt with this. Like, could we use things like navigation start? Like, can we use things, all the navigation metrics? Like, what does that mean in terms of, does this correlate with actually accessible users' behavior? And this part was useful, but when we were discussing it internally with the accessibility team, and when they were trying to make our implementation faster, they desired other metrics. And so we immediately branched off into 3, where we have kind of internal metrics just for Firefox, where we are measuring real details of our implementation that we are not expecting to be applicable to other browsers. But we just needed some measurement to make sure that that work was actually making things faster. So we instrumented our accessibility tree to just give basic timings about when is the first hash push for our accessibility tree. And this was a useful metric for us for when we were doing work to make sure that that work was at least going in the right direction. And so those internal metrics, which are only browser-based, were really helpful in terms of just, are we doing the right thing? Are we kind of going in the right direction? This doesn't really solve the motivating question, which is how can web users test web content without these lab setups? And that is a huge, huge problem. So in discussing it with the accessibility team over, a month or two, or since February, basically, after working through all these problems, I think the kind of consensus emerged that there are two things that would be really useful in terms of what would be useful for end developers. The first thing would be just kind of like, how big is the accessibility tree? Like, what's the node count of the accessibility tree? That's not really a timing. I don't know if that's a performance metric. We don't really have that shape of performance metric currently. And we haven't implemented that yet. But it's a continuing kind of ask because we feel like that would help solve the motivating question. So we'll just put that on the back burner for the moment. But one of the things we thought would actually be useful is kind of like harking back to early WebPerf, which is among the first metrics was time to first byte, right? If you can correct me if I'm wrong, but that's kind of like where things started. And so we really kind of coalesced around this idea of how do we solve that motivating question? That motivating question could be solved by starting in on this idea of time to first speech. And what do we mean by that? We mean accessible user with a screen reader loads a page, and when do they first hear that screen reader start to speak? And this is something that we reach consensus on as generally useful. This is the kind of metric that we think the public would want. However, next slide. We ran into a whole bunch of questions and comments and problems. And we are working on that time for speech, but some of the issues we're running into are, screen reader behaviors are varying per platform. This is not actually part of the browser. This is something that is installed on an OS. Screen readers are different on Mac and Linux and Windows and Android. And they all actually have different behaviors. And we're not quite sure we can configure these screen readers to have the same behaviors across platforms so that we can actually do comparisons. Orca on Linux starts reading or is configured by default to start reading after parsing like equivalent to a paragraph. Windows is like, let's build the whole accessibility tree, and then we're going to start reading. So we're not quite sure we're going to be able to do platform to platform comparisons, but we think even with this limitation, we could do intra-platform comparison. And as we go further down this road and we talk to more people, we are really hungry for some kind of industry feedback. Like, what are other people doing? Are we just off in the weeds here? We are not seeing a lot of previous experience or any kind of, we feel like we're kind of alone here. Like, what else are people doing? There's probably other people are doing some accessibility testing, and is that just they're not doing performance testing, or what's going on? We want to like open kimono here, tell you what we're doing, and we want feedback, and we want to try to come up with industry best practices here. The other thing is we really don't know how we think it's in scope for this group. We don't really know exactly how it's going to fit in with other WebPerf APIs. As I said before, we're basing a lot of this work on nav timing. And we think that, and so we're trying to shape it like that, but we're not quite sure if that's correct. And we don't know if there's a better approach or if there's something obvious we're missing, or if somebody else sees other issues with this, we would just love feedback. That's about it. I would love to hear, from other browser vendors and from other CDM people, like, how are you approaching this issue? Is this something people are working on, or what thoughts do you have?
Yeah, let me stop the recording.